Isaac Newton, and these are my laws of motion. So, my first law is, objects in motion have a tendency to stay in motion unless acted on by an outside force. This is also true for the opposite. Objects at rest have a tendency to stay at rest unless acted on by an outside force. This is only true if the net force equals 0, and you might have heard of this as inertia. Inertia is the tendency of an object to resist change, and mass is correlated to inertia, as in the more mass there is, the more inertia there is. For example, let's say that there are no outside forces like heat, sound, air resistance, or friction. If I roll this ball down the table, it'll continue to move indefinitely unless acted on by an outside force.
Let's take a look at an example. A 15 kilogram box is suspended by a rope. Draw a diagram and calculate the tension in the rope if the crate is at rest, hanging from the rope. In order to solve this problem, we need to use net forces. Since the box is hanging by the rope, there are only two forces acting on the box: the force of gravity and the force of tension. The box is suspended by the rope. The force of tension must equal the force of gravity because the system is at rest. Because of Newton's second law, F net equals ma, or Fg equals mg, we can substitute mass times the acceleration due to gravity for Fg. In order to solve for the tension, we just need to plug in the mass times 9.8, and there you go. The tension of the rope is 147 newtons.
To explain Newton's first law, which is an object's resistance to change, we look to the movie The Martian. In the movie, Rich Parnell attempts to explain to the other characters why a gravity assist will help to accelerate the spacecraft. A gravity assist is a real aeronautical technique used by NASA in the past.
What I'm proposing is we start accelerating immediately to preserve velocity and gain even more.
In which a spacecraft uses a planet's gravitational field to create a slingshot effect and accelerate. Though implementing many different physics concepts such as angular momentum, a gravity assist manipulates a spacecraft's inertia by using a gravitational force to accelerate the spacecraft.
Towards Mars. You're Mars. Now we're going too fast at this point to fall into orbit, but we can do a flyby.
My second law is the net force is equal to mass times acceleration. As you can see from the equation, this means that acceleration is directly related to net force and is inversely related to mass. This means that the more net force you apply to an object, the quicker it'll accelerate, and the mass will have a tendency to resist this motion, as we saw in the first law. To explain my second law, which is F net equals ma, we're going to play a little baseball. In baseball, when I get a pitch, if I have the ball of the same mass, if I swing harder and with more force, I'll accelerate the ball more because acceleration is directly proportional to net force. Whereas if I swing it with less force, it'll accelerate less.
In another example, there is a baseball with a mass of 0.18 kilograms. What is the magnitude and direction of force of the Earth on the ball? Using the equation Fg equals mg from Newton's second law, we can substitute the mass and the acceleration due to gravity into the equation in order to find the force of Earth on the ball and get 1.76 newtons towards Earth.
In order to explain Newton's second law, which is F equals ma, we have a scene here from The Martian in which Mark Watney is disposing of any extra weight he can from his probe in order to maximize acceleration. This is because he needs to reach a target velocity in order to escape Mars' atmosphere and intercept with the main spacecraft. Again, because F equals ma and the thrusters on his probe can only provide a constant force F, in order to maximize acceleration and therefore velocity, he needs to minimize m, or the mass, in order to reach that target velocity and intercept the spacecraft. My third law is that for every action there is a reaction equal in force but opposite in direction. You can see from this equation, the force that A exerts on B is equal but in the opposite direction to the force that B exerts on A.
In order to show you an example of Newton's third law, we brought it to basketball. Watch as I bounce the ball. It bounces up to the same height as when I originally bounced it, even though some energy is lost due to heat, sound, friction, etc. This is because the force of the ground on the ball is equal and opposite to the force of the ball on the ground, causing it to come back to the same height as when I bounced it.
Using Newton's third law, since we know that the force of the earth on the ball is equal and opposite to the force of the ball on earth, we can just simply say that the force of the ball on the earth is equal to 1.76 towards the ball, or negative 1.76 newtons. In order to find the acceleration of the earth towards the ball, we can use the equation F net equals ma. This can be rearranged into the equation acceleration equals the force of earth towards the ball divided by the mass of earth. This comes out to be 2.95 times 10 to the negative 25th meters per second squared.
Finally, to explain Newton's third law, which says that every action has a reaction equal in magnitude but opposite in direction, we look at Mark Watney's final scene in which he rips his spacesuit and uses the escaping air to propel himself towards the spacecraft. The act of ripping the spacesuit creates a thrust force acting in the opposite direction, which Watney is able to control and use to thrust towards the spacecraft.
3.1 meters per second.
And now you know all about my laws of motion. Have a good day.